Introduction. Thanks also for the invitation, as also to Lisa and Taras, as well as thank you all for tuning in. So what I want to do is I want to report on results from 3 papers, which are all joint work together with Panagiotis, Konstantis, and Leopold, Zoller. And yeah, I've just spotted both of them in the audience, which makes me feel a little safer. In case my internet breaks down, then one of them can surely take over. Okay, so this is about GKM theory, and so I was very happy to see that it seems that GKM theory is becoming increasingly more popular. So there were quite a few talks that have mentioned this theory before in these 1.5 days. But still, I think I should start by recalling the basic definitions of GKM theory, as the audience might have shifted a little. Right? So in GKM theory, what one looks at is actions of compact real tori on so compact smooth manifolds. Usually they are assumed to be orientable, and we always have the standing very strong topological assumption that the odd cohomology groups of the manifold vanish. Right. So usually this is this theory is phrased in the context of rational or real cohomology, but so the examples we will see later on, they will all satisfy the slightly stronger condition of vanishing odd integer cohomology. Sometimes one then speaks about integer GKM manifold. Right? So this notion goes back to a paper by Goertsches, Goertsches, and McPherson. Right, so what does one do? One assumes that the one skeleton of the action, meaning the set of points whose orbits are of dimension at most 1, is as simple as possible. Right? And means for the fixed point set that we assume that we have only finitely many fixed points around. And it means something for the points with orbit dimension 1, which we can phrase in several different ways. One way to phrase it is by saying that the one skeleton is a union, a finite union of T invariant 2 spheres. But we can also phrase it in terms of the orbit space of the one skeleton, right? So if I project the one skeleton, right? So here it is again, to the orbit space here, then I get something that is homeomorphic to a graph, right? So in other words, so M1 is the union of T invariant 2 spheres. All of these 2 spheres are necessarily fixed by a codimension 1 subtorus. So they're up to a coordinate change. So we have the standard action on any of these 2 spheres, and collapsing them results in just a closed interval, which I now regard as an edge in a graph. Right? So what does one do in GKM theory? One associates to such an action exactly this graph, but with some additional structure, namely a labeling. Right? So, and what kind of labeling do I want to put? I want to put labels to the edges of the graph. Right, so to explain what this label is, so remember any edge corresponds to an invariant 2 sphere, right? And inside this invariant 2 sphere, you then have precisely 2 fixed points of the torus action, and then the 2 sphere corresponds precisely to a 2-dimensional subrepresentation of the isotropy representation in that fixed point, and this 2-dimensional subrepresentation then has a weight, and this weight we put as a label. And now there is, one has to distinguish 2 cases. So I think Taras already asked about this after Michael's talk yesterday. If we don't have an almost complex structure fixed, then these weights are only well-defined linear forms on T up to sign, right? So if I don't have an almost complex structure fixed in my 2-dimensional subrepresentations, I cannot distinguish between clockwise and counterclockwise rotation. So my weights are only well-defined up to sign. But if I have an invariant almost complex structure fixed, then these weights are honest elements in T star. Okay, so this is my GKM graph of the action. It's always an n-valent graph. And maybe the first example that comes to mind is that any toric symplectic manifold is automatically a GKM manifold. And one can directly see what the graph looks like. Namely, you just look at the momentum image of the manifold, we know that it is a polytope, and we know that the dimensions of the faces of the polytope correspond precisely to the dimensions of the orbit of the action, right? So in other words, the orbit space of the one skeleton of the action is nothing but the one skeleton of the momentum image. Right? And what are the labels that we put? So we also know that when you have a toric symplectic manifold, then the weights of the action are encoded in the slopes of the edges of that polytope. Right? So when you have an edge in this momentum image, then you take a primitive vector pointing in the direction of the edge and put this as a label. Right? So this is a very important class of examples. Right? Okay, so what will be important, because I want to talk about realization results. So far I've explained how to pass from geometry to some combinatorial object, to some graph. Now I want to go the other way around, and for that I need a notion of abstract GKM graphs that do not necessarily come up a priori from an action. Right? So this notion is due to Guillemin and Zara, and again it comes in two forms, depending on whether you want to model something that has an almost complex structure or not. Right, so let's read this with the red words, then we model the situation without complex structure. And we talk about an unsigned GKM graph, if one wants to emphasize this. We just take an n-valent connected graph and a labeling, which is then usually called an axial functions in their terminology. What does it do? So it associates to any edge with something that might become weight of some representation. And then this first condition just is this original the GKM condition that the one skeleton is just a union of two spheres, translated to the level of the graph here. It means that the labels of any two edges at a vertex are linearly independent. Right? So in the notion of Anton's talk yesterday, this is the same as the weights being in two general position. Right? So that was his way of phrasing this condition. Right? And then there's another condition here, that of a compatible connection. What's that supposed to mean? For that, I have drawn this picture down here. Right? So a connection does the following. So when you fix an edge E here in the picture, right, then the connection nabla E is a way to transport edges that start at the initial vertex of E to the terminal vertex of E. Right? So it's a bijection from the edge set at this vertex here to here, and for every edge E we have one such bijective map, right? And then the weights of these three edges should satisfy this relation here, right? So the weight here differs from the weight here only up to sign and some integer multiple of the weight down here, right? So how should one think about this condition? Right, when you look at the tangent bundle of the manifold here, then it becomes an equivariant vector bundle. And then when you restrict it to the two sphere that belongs to the edge E, right, then so a little bit roughly, what you do is you decompose it into equivariant rank 2 subbundles. And then this edge F here corresponds to one of these subbundles, and then you follow the subbundle all the way to the other fixed point, and then you again have a two-dimensional vector space in that subbundle, and you take the weight there, and you compute that they have to the weights have to be related in this way. Okay, so this is an abstract condition on the weights the graph has to satisfy, right? And the last one is just that the weight changes sign if one is in the sign setting. When you pass from one fixed point in the sphere to the other one. Right? Okay, so we have these two notions of GKM graph, an unsigned one and a signed one. Okay, so maybe to warm up, I want to have a look at dimension 4. Dimension 4 is maybe not the dimension in which one usually does GKM theory, because I mean, we need a two-dimensional torus acting here, and when we have two-dimensional tori acting on 4 manifolds, then of course it's an action of complexity 0, and of course we have other methods to deal with this situation, right? We don't need GKM theory to treat this dimension, but still to warm up, I think it's good to illustrate these notions in this dimension. Okay, so let's start with the maybe most known special case. When you have a toric symplectic 4 manifold, and of course we know they correspond to two-dimensional Delson polytopes, right? So here are some of them. But now I'm interested in GKM theory. So I'm not really interested in a polytope. I'm interested in the associated graph. Right? And so I've already explained how to go from here to a graph. Right? So we just forget that these things are polytopes. We just, in this case, keep the boundary of this polytope as an abstract graph together with the labeling. And remember, how is the labeling defined? So the labeling, right, at any such edge is given by the primitive vectors pointing in direction of the edge. Yeah, so these primitive vectors, right? So in other words, we forget about lengths of edges, right? So the associated GKM graph is precisely this, but we forget about lengths of edges and just keep the directions of these edges, right? Okay, so of course we know that when we modify the symplectic structure on these toric symplectic 4 manifolds, then the Delson polytopes change, right? For instance, if you look at the CP1 times CP1 here, and you rescale the symplectic structure in these two forms, then you rescale the corresponding edges here, and you get rectangles of different size, right? And all this information is lost when you pass to the GKM graph. So the GKM graph doesn't keep track of this particular symplectic form. So it might look like that the GKM graph doesn't really see that this is in fact the toric symplectic manifold. But that's not entirely true, because it is somewhat, yeah, so there is still some information from the symplectic information being kept, because it's a restriction on the graph to be realizable as the boundary of a polytope. Like, for instance, have a look at this graph, right? So this is also a signed GKM graph, but it's not the one skeleton of a polytope, right? So how do I want to read this picture? So this is not to be seen symplectically, right? So this does not live inside the dual of any Lie algebra now, but I want to read this picture in the same way as before. So I don't write labels, I just have the labels implicitly defined by the way I drew this graph. So for instance, the label of this edge attached to this vertex here is 1, 0, because this points in direction of the x-axis, right? Okay, so in this way, you see that this is a signed GKM graph, right? So when I slide an edge here along this edge, I get this edge, so, and it points in the right direction, right? In the same direction. So I don't flip to the other side. So the signed GKM condition is still satisfied, right? So this here is a signed GKM graph that cannot come from a toric symplectic action. Now, on the other side, on the other hand, I also have unsigned GKM graphs, right? So what's this? I guess everybody knows this. This is the T2 action on S4, which is an unsigned, which does not have an invariant almost complex structure, not a complex structure at all. But it is still GKM, so it has an unsigned GKM graph, but which cannot be given a signed structure. Okay, so let me summarize how the geometry of these GKM spaces leave their mark on the GKM graph, right? So we have the polytope type graphs, so that's what we call these graphs that come from a Delson polytope. They are realized by toric manifolds. This is just Delson's theorem. We have the unsigned situation. They are realized by S4 or quasitoric. Yeah? So this is just the case where you have this biangle from before with any choice of unsigned labeling. And if you have an n-gon for n bigger or equal to 3, then they are always realized by a quasitoric manifold. Right? So how can you see this? You just take this n-gon, and then of course you can abstractly take this n-gon as the boundary of something that's right, homeomorphic to a two-dimensional polytope. Right? And then the labeling of the edges is just the same as a characteristic function, right? So it's the same as prescribing the isotropy groups of the edges. So in this way we can construct in the classical way the quasitoric manifold associated. Right? And when then you have this intermediate case here, the signed setting, right? And then one can easily observe that to put a signed structure on this graph, right? So to give the labels well-defined signs is the same as just a reformulation of putting an omni orientation in the quasitoric manifolds, and then there's a result by Kustarev which says that when you have a signed structure here, or when you have an omni orientation, then you have an invariant almost complex structure. Okay, so these three types of GKM graphs are realized by four-dimensional T2 manifolds with corresponding type of geometric structure. Okay, so much for dimension 4. As I said, dimension 4 is not really what one is after here. So I want to move up to real dimensions. So the rest of the talk will be about dimension 6. And I want to start the discussion about dimension 6 with my very favorite T2 manifold. So my very favorite maybe Lie group action, or maybe even my favorite manifold. So this is Eschenburg's twisted flag manifold. It's an example of a biquotient. Right? So I guess everybody knows homogeneous spaces, which arise in the way that you take a Lie group and you take a subgroup and you take the action of the subgroup from right or from left, which then automatically is free, and then you take the quotient, and that's a homogeneous space. And so when you look at biquotients, then you do something similar. You take actions of groups on Lie groups, but you don't act from one side, but you act so say from the left and from the right. And this is maybe one of the simplest non-trivial examples of a biquotient. Right? You just take T2, so two unit complex numbers, and they act on a matrix in SU3 in this way here. Right? So what's not obvious now is that the action is free, but one can check this and look at the quotient space, and then you get a manifold. This is called Eschenburg's twisted flag. So notation here is a bit strange, so this has nothing to do with symplectic reduction, but I don't want to write just one slash, because one slash would then look like the standard flag SU3 mod T2. Okay, so SU3 mod T2 and this manifold, they are very similar in some respects, but they are not the same manifold, right? So for instance, one can check that their cohomology groups are isomorphic, so say over there. Doesn't matter, over the reals, over the integers, they are isomorphic, but their cohomology rings are not isomorphic. So these are really not the same manifold. And I claim that these two manifolds also have other things in common, not only their cohomology groups. They have various geometric things in common. Yeah, so several will turn up now in the next couple of minutes. So, so one thing is that also this space has some symmetry, right? So we have a maximal torus of SU3, and it still acts on this Eschenburg flag, for instance, just by left multiplication, right? So we take maximal torus here, the action by left multiplication commutes with this action here, right? Because everything is just diagonal matrices. So this gives a well-defined action on here. Okay? So on the other hand, we have this action which we wrote down in order to define the Eschenburg flag. And we can observe that this action extends to an action of a larger group, namely of the Lie group U2. Right? So how's this action defined? You take a matrix in U2 here, and you let it act in this way. And you see when you put a diagonal matrix A here, right, ST, then you recover precisely the action from up here. Right? And then, yeah, so because the T2 action here is free, also this U2 action is free. And we can look at the quotient with respect to this action, and we obtain a T2 equivariant fiber bundle here. Right? So this space, the Eschenburg flag, in fact, lives here as the total space of a CP1 bundle over CP2. Right? So how does one see that this thing here on the right is CP2? Right? So you can first quotient by SU2. Right? When you look at the SU2 sub-action here, then this is just the standard SU2 action here, right, on the upper left. So you get S5, and then you have a residual circle action on this S5, which gives you CP2. Right? So this is one thing this space has in common with the standard flag. Also, the standard flag fibers as a CP1 bundle over CP2. But of course, it's a different.
Excuse me, Oliver, that's Taras.
Yes.
Is this CP1 bundle of the fiber, is it a projectivization of some plane bundle, complex?
Yes, it is. Bundle? So this will actually, I will come to this soon. Yeah, it is.
Oh, thank you.
Okay, so, but maybe I can directly explain how this C2 bundle arises, right? So you look at this action of U2 on SU3 as described here, right? And you just take the twisted product with the standard representation of U2 on C2. Right, so U2 acts on, so now I would like a blackboard, but there is none. So U2 acts on SU3, right, just via this action, and also on C2 via the standard action, and you just take the twisted product. This gets a complex rank 2 vector bundle over CP2, and this is its projectivization. Okay, so we have this fiber bundle here, and we can look at its GKM theory, because one can easily check that this space is GKM. So maybe this was a bit fast. So I explained 2 slides ago that this Eschenburg flag here also admits a T2 action, right? So what was this T2 action? You just take the maximal torus in SU3 acting from the left by just standard multiplication of diagonal matrices. And then one can check that this action is GKM, right? And when one can just compute the weights in all the isotropic representation and determine its GKM graph, and what one gets is this picture here on the left. Right? On the other hand, one sees that this T2 action on here also commutes with this projection here, right? So let me go back here, right? So the T2 action also commutes with this action here of U2, because on the left, I still just have diagonal matrices. Here I have something non-diagonal, but on the left, I have only diagonal matrices, right? So this commutes here. So I have a T2 equivariant fiber bundle here. Right? And now I claim that this T2 equivariance of this fiber bundle leaves its mark on the GKM graph, namely the GKM graph also fibers over the GKM graph of the base. So, and the GKM graph of CP2 is just this standard triangle here, right? So this notion of a GKM fibration was introduced by Guillemin, Sabatini, and Zara. I don't want to give the precise definition, because in this very special 6-dimensional situation, fibering over something 4-dimensional, it's very easy to just verify ad hoc the conditions that are satisfied. Right? So what's this GKM fibration here? Right? So it's a map on vertices, first of all. Right? So we see so we have 3 pairs of vertices that are mapped to 1 vertex each here. And at each vertex here in the total space, I have two edges that sort of correspond uniquely to edges here in the base, and they have precisely the same slope. So meaning in the sense of GKM theory, they have the same labeling, right? And I have one additional vertical edge here, which does not correspond to anything here. So the fibration on the level of edges is just a partial map, which, right, so sends edges here at one vertex bijectively, so a subset of the edges bijectively to the vertices at the corresponding base point, right? And then one also needs a condition on compatible connections, right? So which here in this situation is just that we can find a compatible connection here in the total space that respects horizontality and verticality of edges, right? So that when I, for instance, slide along this edge, then this vertical edge here is sent to this vertical edge here. This is okay. So this is the everything that's needed to have a GKM fibration in this setting. There is in higher dimensions, this definition becomes a little more complicated. So one has to distinguish between GKM fibrations and GKM fiber bundles. But all this is not relevant in this low dimensions. So I will not go into detail. Okay, so I claim, so on the one hand, we have this fiber bundle structure here, which so to say, gives more information on the GKM theory. On the other hand, this fiber bundle structure here also gives information on the geometry of that space. And let me mention two aspects of this. So first of all, the fact that this here is an equivariant fiber bundle of this type, and that tells us that this manifold admits a T2 invariant symplectic structure. So this is what's sometimes called a symplectic bundle, right? So we have as a base, we have a symplectic manifold here. As a fiber, we have a symplectic manifold. And then under certain conditions, we can construct a symplectic structure here on the total space. Essentially, what one does is one finds a form that maps to the symplectic forms on the fiber, and then complements it with a large enough multiple of the symplectic form on the base to get a symplectic form here. So that's a construction that was first used by Thurston. So in this way, we get an invariant symplectic structure here. And on the other hand, this manifold also has a Kähler structure. Why does it have a Kähler structure? Right. So as I mentioned before, this thing is the projectivization of a complex rank 2 vector bundle over CP2. But it's known that every complex rank 2 vector bundle over CP2 admits a holomorphic structure. And when you projectivize this bundle, then you get a Kähler structure. Right? But this Kähler structure then has nothing to do anymore with this action. Okay, so this was, so say the first of our papers. So we looked at lots of biquotients here. So this is just the simplest example of the biquotients we looked at. And introduced symplectic structures and also a few Kähler structures on them. We found this interesting because biquotients previously were considered only in the context of Riemannian geometry. Right? So Eschenburg introduced them or classified also lots of them because he was interested in finding manifolds with positive sectional curvature. Right? So this example here is also one manifold with positive sectional curvature. So we found it interesting that they are also of relevance in symplectic and Kähler geometry. Okay, and then so one day a master student of mine, so Maximilian Schmidt, pointed out to us that he had seen this picture here on the left before. So he pointed out to us that it already appeared 20 years earlier in a paper by Susan Tolman, in which she constructed so the first Hamiltonian, so 6-dimensional Hamiltonian T2 manifolds that do not admit an invariant Kähler structure and with finite fixed point set. Right? So let me very briefly explain her construction of these manifolds. So this is a slight modification of her example due to Woodward, but the idea is due to Susan Tolman. So she took two T2 invariant Kähler manifolds. Here on the left, here I drew their momentum images or X-rays, as she calls it, with the interior edges and vertices here. And then she cut these manifolds in two halves, as indicated by these dotted lines here. Right? So so she took the pre-images of the lower half here and of the upper half here and glued them symplectically to obtain precisely this picture here. So which then arises as the momentum image of some Hamiltonian T2 manifold. Right? So, and why was she interested in this picture? It's because she could show using the shape of this picture that this manifold cannot admit an invariant Kähler structure. So very roughly, the argument used the theorem of Atiyah, which gave information on the images of torus orbit closures of the complexified torus, which still acts if the action was Kähler. Right? And the condition is something like this. So when you sit down in a vertex here and you pick here these two edges, then you look at the cone, which is cut out of this picture using these edges, then this cone should look like a subpolytope of this thing, but it doesn't here because I hit this edge here in the wrong place. Okay, so this is, yeah, so this was some coincidence that suddenly here the same momentum image appeared. So we thought maybe these examples are in fact the same, just constructed in a different way. One motivation to think about this problem was also that she posed as an open question in her paper whether this manifold she constructed in this way does admit any Kähler structure at all. Right? And on the other hand, the Eschenburg flag, it does admit one because we constructed it as the projectivization of some vector bundle. Right? And yeah, so this is contained in our second paper. We were able to show that these two manifolds are in fact non-equivariantly diffeomorphic. So in particular, Tolman's example does admit a non-invariant Kähler structure. And so how did we show this? Very briefly, we used GKM theory. Right? So we combined GKM theory with the diffeomorphism classification of manifolds in dimension 6. Right? So when you have a manifold in dimension 6 with vanishing odd degree cohomology, then this is result of Wall, Yupp, and Zuber. The diffeomorphism type is determined by only topological invariants. So by the cohomology ring, the second Stiefel-Whitney class, and the first Pontryagin class. And all this data is encoded in the GKM graph. Right? So we have heard before that the GKM graph encodes equivariant cohomology and then also ordinary cohomology because of this equivariant formality condition, but it also encodes the characteristic classes. So here in this setting, one has, I mean, the main subtlety here is maybe that one has to work over the integers, and over the integers, everything is a bit more complicated than over the rationals. So for instance, we use a variant of the Chang-Shelbrett lemma, which was already appeared in Michael's talk. So we use the variant for the integers due to Matthias Franz and Volker Puppe, which works under certain assumptions on the isotropy groups, but which are satisfied here because all isotropy groups are connected in this example. Okay, so this is the situation now. So we have these beautiful examples. They arise as, so as I said, as projectivizations of certain vector bundles over four-dimensional T2 manifolds. On the one hand, this tells us that the graph, the GKM graph, has a certain structure. On the other hand, we saw that this structure as a projectivized vector bundle gives us interesting geometry on the spaces. Right? So we had the idea to sort of relate the GKM theory, so the fact that GKM graph fibers over something else, to geometry. Right? So staying in dimension 6, we asked ourselves, so what kind of GKM fibrations are there, and are they always realized by maybe by projectivizations of vector bundles, and do they always have the same kind of geometric structure? So this is the type of questions we addressed in our third paper from this year. Okay, so first thing we did is that we classified all GKM fibrations in this dimension and of this type, meaning we looked at three regular GKM graphs, right? So 3 valent graphs that fiber over 2 valent GKM graphs, so in other words, n-gon. First thing one observes is that when you neglect the labeling, so you just look at the graphs, the naked graphs, then there's not much choice for these graphs, right? So you have only 2 possibilities, right? So picture these graphs as fibering over an n-gon, right? Here, so I didn't draw the n-gon, but you see it here, right? So then there's not so much choice if you want the graph to be 3 regular, right? So over each edge in the base, you just necessarily have a quadrangle, and then you have all these quadrangles lined up after each other. And the only choice you have is whether you glue them together like a cylinder, as indicated here, or like a sort of graph theoretical Möbius band here, as indicated here. Right? So as the so just on the level of graphs, this is all you can do. Right? And then, of course, you have much greater flexibility when you look at labels. Right? So we classified all possible labelings of these graphs. So here is again a GKM fibrations. I just drew one portion of it. Yes, I just look at the fibration locally. So I don't care about whether this thing is of twisted type or of product type at the moment. So then this GKM fibration notion tells us that the horizontal weights here and here, they are the same as the weights down here. Right? So in order to understand the labels here, right? So I keep the base graph as a given datum, and I try to understand what are the possible total spaces here. So I just have to understand how these fiber weights alpha I look like. Right? And then, yeah, what can one do? Right? So because this here is an effective 2-valent GKM graph, at every vertex, the adjacent edges here, they form a basis, right, of the integer lattice. Right? So I can write these fiber weights as a linear combination of these weights of the horizontal of the basic weights, right? And then I can use the GKM condition to compare the coefficients. And yeah, what's the result? So this is a rather short computation that one finds n non-vanishing integers ki, so that I can write these fiber weights alpha I in this form. Right, so every such ki appears now twice in such an equation, right? So for exactly 2 of these alpha I. So I'm leaving out the subtleties here because one has to be careful in the end whether this thing is twisted or not, and then one how these equations here glue together at the boundary. But yeah, so essentially this is it, right? So okay, so what I'm sweeping under the rug is here. So how do K0 and Kn behave with respect to each other? So maybe there's a sign change, but that's not so important here. In the end, what we get is that for a fixed base graph B, the set of 3-valent GKM fibrations here is in one-to-one correspondence to this set. Right, so the ki here are just the coefficients, and then we have this number eta, which is 0 or 1, which just indicates whether my graph is of product type or of twisted type. Right? So I have very many GKM fibrations for any given base graph B. Right? Okay, so let's give 2 examples to get a feeling what kind of numbers appear here. Right, so here is the Eschenburg flag again. Right? So I look at one of these fiber weights, say these alpha I here, alpha 1 here, and I write it as a linear combination of the adjacent base weights. So we see alpha 1 is gamma 3 minus gamma 1. Right? And I can do the same for the other fiber weights here. And from this, I can directly read off these numbers ki. And the graph is of twisted type, so I put a 1 here. And so how should I read this example? I should read it the other way around to make it more interesting. I start with CP2, and I just prescribe these 3 numbers here together with, and I demand that I want to construct a twisted GKM graph. And I'm immediately led to this example here, which, as I said, determines the Eschenburg flag or Tolman's example up to diffeomorphism. Okay, so what happens when I change one of these numbers, right? So for instance, let me change the third of these k's here to +1. Then we get this example, namely the standard flag, right? So one can do the same computation. So just changing a single number here in this ki results in drastic changes in this graph. So again, so this is well-known GKM graph of the standard flag, which is again twisted. So we have a 1 here, and it corresponds to these numbers. Okay, so now I have a large variety of GKM graphs available, and now I'm interested in whether these things always arise as from geometry, right? So what I want to do is want to solve the GKM realization problem for GKM fibrations, where we have fibrations as before. And we want to show that they are always realized by projectivizations, right? So essentially what we want to do, we want to look at pictures like this, start with a base graph here, and then draw some picture like this, right? So we follow the base weights here. Say we want to construct something twisted, so I have to cross one of the edges here, and then I follow the base graph once more, and I get this nice fish-like picture here. Right? So this is GKM theory here, but in the end, we also want to construct geometry on this, so in particular symplectic structure. So in particular, what we want to do with this idea is to construct Hamiltonian non-Kähler 6 manifold with a prescribed momentum image. Right? So I want to just draw this picture and then say there exists a Hamiltonian manifold which has exactly this momentum image. Okay, and this is precisely what our theorem does. So we start with a GKM fibration, which has one more adjective here, which I explain in a minute. And then it's geometrically realized as the projectivization of such vector bundle. So fiber-wise signed, what's this supposed to mean? So before I said we should distinguish between signed and unsigned, right? Where the signed graphs correspond to invariant almost complex structures, whereas unsigned corresponds to the pure topology. Right? So here we will end up with projectivizations of complex vector bundles. So the fibers of these projectivizations, they are naturally CP1s. So they naturally come with a complex structure. So meaning the fiber weights automatically have a well-defined sign, right? And this has to be modeled in the GKM data I start with, right? So I will not give the formal definition now, but what one can do, one can just put unsigned labels to all edges, except for the fiber edges, they should have a well-defined sign. And then I demand also the GKM compatibility relation between the weights with the appropriate sign when I slide vertical edges to other vertical edges. Okay, but if I'm interested only in spaces with more geometry, then I can forget about the fiber-wise sign condition, and I can just look at fibrations of signed graphs, right? They are in particular fiber-wise signed. And then this thing turns out to always admit an invariant almost complex structure. And if I have more, if my base is of polytope type, right? So if it's the boundary of a two-dimensional Delson polytope, then this projectivization admits, similar to the Eschenburg flag, Tolman's example, a T-invariant symplectic structure and a Kähler structure. And in many cases, we can do the same thing as Tolman did. We can show that this space does not admit an invariant Kähler structure. Yes, so what does many cases mean? Many cases means essentially that the base graph does not have 4 vertices, and that the total space, when I realize it, so when I look at these pictures here as before here, I have as many interior vertices as possible. And so this is an example where this most cases applies. Okay, so I have one more slide about the proof, but maybe I'll just say orally in 2 words how the proof works. So first thing we do is we realize B. So that I explained in the beginning, right? So we can always realize n-gons by 4-dimensional T2 manifolds, right? S4 or quasitoric. I explained that at the beginning. And then we have to construct this bundle. So we do this in 2 steps. We construct the bundle first over the 1 skeleton of X. And we construct an equivariant vector bundle. We do this explicitly over the 1 skeleton. So then we have a vector bundle just over X1, and then we somehow have to extend it into the interior. And to do that, we use equivariant obstruction theory, which tells us just abstractly that there always exists an extension to the interior. What this extension then really looks like, we don't really care, because we only want to realize the given GKM data, and the given GKM data is already prescribed by the shape of this bundle over the 1 skeleton. Okay, and then I have to construct the geometric structure, but this then is not so different as in the example of the biquotient, right? So for instance, this construction by Thurston to construct the invariant symplectic structure goes through just as before. One word about this in many cases at the end, so already in Tolman's paper, so to show that with the given, so when you look at the symplectic structure, then her criterion using Atiyah's theorem was directly applicable to this picture, right? So you remember this criterion, you cut out the cone, and then this has to be a subpolytope. It was directly applicable there because we have chosen a fixed almost complex structure. We have a compatible almost complex structure which gives you the signs in the graph. If you're interested in the question whether you have any invariant Kähler structure with an arbitrary invariant almost complex structure underlying, then it was more work. So she had to look at all possible arising X-rays which is compatible with the 1 skeleton of the action. And we sort of do the same thing. So we have to classify all possible signed GKM graphs that have the same unsigned GKM graph as the one we started with. Right? So this is a relatively subtle here. Okay, so I think that's all what I wanted to say. Sorry for going a little bit over time. Thank you.
Okay, so let's unmute the phone. The mic.